Good evening, everyone. I am Soumak Nag, a research scholar at School of Mathematics and Statistics, University of Hyderabad. So today I will do problems from partial differential equation. So let me first write the name of the course and course ID. The name of the course is partial differential equation, and course ID is. So now I will solve some problems from partial differential equation. So let me first begin with a boundary value problem from ODE, ordinary differential equation. The first problem is, let lambda is a real number, and consider the boundary value problem d2y dx2 minus lambda y is equal to 0 with the boundary conditions are there that y at 0 is 0 and y at pi is also equal to 0. So from the options given below, identify all the values of lambda for which the boundary value problem has a non-trivial solution. From the options given below that I will write now, identify all values of lambda for which the boundary value problem has non-trivial solution. So the options are, so my first option is options are -4, option A is -4, option B is -2 pi, option C is -1, option D 0, option E 1, option A 4. and option G also 2 pi. So now I want to solve this problem. This problem is a second order boundary value problem for which non-trivial solution exists. So answers. Since it is a second order differential equation, so let me write it quite clearly. Since it is a second order differential equation, so it is d2y dx2 minus lambda y is equal to 0. So now we know that for this type of equation, let y equal to e power mx be a trial solution of this equation. E power mx be a trial solution. So the auxiliary equation becomes so the auxiliary equation is, since y equal to e to power mx, so dy dx is m e power mx and d2y dx2 is m square e power mx. So it is m square minus lambda into e power mx equal to 0, but e power mx is non-zero because e power something is non-zero. So my auxiliary equation becomes m square minus lambda equal to 0. So now for different values of lambda we get different conditions, that is lambda may be positive, lambda may be negative, lambda may be 0. The three cases will arise. So let me consider the case 1. Case 1 is that lambda is positive. So in that case m square minus lambda equal to 0 implies lambda m equal to plus minus root over lambda. So if m equal to plus minus root lambda, my solution is yx equal to c1 e power root lambda x plus c2 e power minus root lambda x, where c1 and c2 are arbitrary constants. So now my condition is given as y0 is 0 and y of pi is 0. So by putting y0 equal to 0, I get that c1 plus c2 equal to 0 and y pi equal to 0 implies c1 e power root lambda pi plus c2 e power minus root lambda pi equal to 0. Now we have to solve these two equations to find c1 and c2. Now the determinant is that 1 e power root lambda pi and e power minus root lambda pi is equal to e power minus root lambda pi minus e power root lambda pi, which is a non-zero quantity. So by solving this equation we get that c1 equal to c2 equal to 0. Both c1 and c2 are 0. So I get the solution as c1 equal to c2 equal to 0 because the determinant is non-zero. The coefficient determinant. Determinant means the coefficient determinant. So c1 c2 equal to 0, but it gives yx equal to 0, which is a trivial solution, which is not our case. It is a trivial solution. We want a non-trivial solution for which the solution exists. So let us move to case 2, where case 2 where lambda is equal to 0. So my case 2 is that lambda equal to 0. So in that case I got m square minus lambda equal to 0 is my auxiliary equation. So I will get m square equal to 0. Now it implies m equal to 0 comma 0. So the solution yx is c1 plus c2 c1 sorry, let me just clear this. So my solution becomes c1 plus c2 into x into equal to 0. C1 plus c2 into x into e power 0x. E power 0x is simply 0. E power 0x is 1. So c1 plus c2 into x into e power 0x. That is c1 plus c2x. This is my solution. Now, this solution again satisfies the boundary condition, that is y0 is 0 and y pi is also equal to 0. So by putting y0 equal to 0, I get that the solution is, I get that condition for c1 is c1 equal to 0, and for y pi equal to 0, I get that c1 plus c2 pi equal to 0. Since c1 is already 0, so I get c2 pi equal to 0, but pi is non-zero quantity, so c2 equal to 0. So I get again, in this case also I get, again in this case I get y as a y equal to 0. So it is also again a trivial solution. So yx equal to 0, but we are looking for non-trivial solution. So I will consider the case 3 where lambda is negative. So now I turn to case 3 where lambda is negative. So in that case my auxiliary equation is m square minus lambda equal to 0. Again, since lambda is negative, so m becomes plus minus I root over minus lambda. So in that case, since complex root are coming, that is purely imaginary roots are coming, so I get the solution as yx equal to c1 cos root over minus lambda x plus c2 sin root over minus lambda x. So these c1 and c2 also satisfy, these c1 and c2 also satisfy the condition that y of 0 is 0 and y of pi is also equal to 0. So I get the solution as, if it is satisfied y0 is 0, then sin 0 is 0, so I get c1 into cos root over minus lambda pi equal to 0, not into 0 plus c2 into 0 equal to 0. So that implies c1 equal to 0, and y of pi equal to 0 implies c1 equal to 0, so y of pi equal to 0 implies c1 sin root over minus lambda pi is 0. But if c2, now two cases will arise, because if c2 equal to 0 and sin root over minus lambda pi equal to 0. Now if c2 equal to 0, then my solution becomes again a trivial solution, so I will neglect this case. I consider sin root over minus lambda pi is 0. Now, so sin root over minus lambda pi is same as sin n pi, where n is a whole number. That is, n starts from 0, 1, 2 to infinite. So this implies that root over minus lambda pi equal to n pi. So it implies, that lambda equal to minus n square. But I take lambda positive, so I will take n from 1 to up to n. That is, n is a natural number. So I get that for lambda equal to minus n square, the solution are non-trivial, which I was looking for. So in so my so my here n is a natural number, that is n equal to 1, 2, 3. These are the numbers. So using now I will look for the uh, what are the options given. So my option is that -4 and -1 are the right option, because all other will not be considered as minus of n square. So, so lambda equal to -4 and lambda equal to -1 are are the correct options. This is the this ends with first problem. So now I will consider problem 2. Problem 2, that says it is again a differential equation, ordinary differential equation problem. It says that let f be a function which defines on R to R, that is real value function which is a continuous. Let f, and let phi be a differentiable function. Phi is a function of x only. Then uh, which is defined, now phi is defined on the interval 1 comma 3, and phi satisfies some differential equation, that is phi is defined on the interval 1 comma 3 and uh, satisfies a differential equation f of px. Derivative of phi is function of f of px. And now I considered another function xi. Xi is, let xi be another function which is defined from 0 comma 1 to the interval 1 comma 3, where phi is defined, such defined by defined by xi of t equal to 2t square plus 1. So now again define another function. More functions are coming in this problem. So another function I define, that define another psi t, define psi, which is defined by psi as a function of t, such that psi equal to phi of xi t, composition of two functions, where psi is defined on open interval 0 1. So for t is in open interval 0 comma 1, psi is defined by psi of t equal to composition of two functions, phi composition with xi of t. Then now I am differentiating psi with respect to t. So d psi dt is equal to at into function of psi t. Now my question is, what is at? Question is, what is a of t. So the options are giving us, first option is 4t, option A t is equal to 4t, option B is root over 1 minus t by 2, option C is 1 minus t by 2, and option D is 2t square. So now I will solve this problem. So f is a function and phi is a differentiable function. So f is a given function from R to R, and phi is a differentiable function. F is a continuous function, and phi of x is a differentiable function, which is defined by which is defined by d phi of x equal to a function of phi of x. So here again I define another two functions, xi and psi. Xi is defined as xi from open interval 0 1 to 1 by 3, which is defined as xi of t equal to 2t square plus 1. And I am defining another function psi in the next slide. So psi is defined from open interval 0 1 such that psi of t is composition of two functions phi with xi. So now I will differentiate psi with respect to t. Yeah. Ddt of phi of xi t. This is xi. So here I will get that first I will differentiate with respect to xi t, and then I use the chain rule. First, so I am differentiating using, I am using the chain rule from calculus of one variable. So I get the solution as phi dash of xi t into xi dash t. So you first notice that function f is defined as ddx of phi x equal to f of phi x. So here dd xi of phi of xi t is same as f of phi of xi t, because I just replace phi x by phi of xi t, that is x is replaced by xi t only. So I get that f of phi of xi t into xi t is given by 2t square plus 1. So ddt of 2t square plus 1. ddt of 2t square plus 1. So uh, now f of xi t is same as f of phi of xi t is same as f of psi t, because psi t is defined as composition of two functions, and ddt of 2t square plus 1 is 4t. So I get as at into f of psi t. So I get at as 40, which is my option A. So the answer is at equal to 40 is the required answer. This solves the question number 2. Now I will consider another question, that is on partial differential equation. These problems is a partial PDE problem. It is question number 3. So it gives that let u be a partial, it has two independent variables. So u be a function from R2 to R which is differentiable. Let u be a differentiable function which is denoted by u is a function of two independent variable are there. So u equal to u of x comma y, and further assume that u satisfies this differential equation, this linear PDE ux x comma y plus uy of x comma y is equal to 0 for every xy is in R2 with a condition is that u of x comma 0 is sin x. This equation is true for all x comma y in R2 plane, and u x 0 equal to sin x for every x belongs to R, for all or for every x is in R. Then I have to find what is u0y. Then question is for y is in R, for y belongs to R, u0y is what? What is u? What is u of 0 comma y? The options are given as option A is 0, option B is minus sin y, option C is cos y, and option D is minus cos y. So now I will solve this problem. So the differential first order linear differential equation that u satisfies is ux x plus uy is equal to 0 for all xy is in R2 and ux comma 0 is 0. So by Lagrange's method of solving first order linear differential equation, first order linear partial differential equation, we have the coefficients dx by the coefficient of ux, that is 1, and dy by coefficient of uy 1 equal to du by 0. So now I will compare these three equations to get two functional equation. Then I will conclude the resulting u as the functional dependent of the other one equation. That is, suppose I consider the first two ratios. So considering the first two ratios, I get that I get dx by 1 equal to dy by 1. So I get, so the solution becomes x minus y equal d. Now I integrate both sides. So integrating I get x equal to y plus some c1 constant. So x minus y equal to c1, and considering last two ratios, now I consider the last two ratio here. So considering the last two ratios, I get that dy by 1 equal to du by 0, which implies u equal to, and du equal to 0, so implies that du is 0. I just cross multiplication, and which implies u is equal to another constant c2. So my solution becomes, the general solution of this, the general solution of the PD, the given PD is uxy equal to function of x minus y, right? Phi is a differentiable function. So phi is a differentiable function. Now, now I will consider the, what is the initial condition is given. Initially it is given that u of x comma 0 is sin x. So my I am putting these values in the my solution, general solution. So I will get ux0 equal to function phi of x. So I get the phi of x equal to sin x. So phi of x minus y is sine. I just replace x by x minus y. It is sine of x minus y. So my solution of the given PD becomes ux comma y equal to sine of x minus y. Now I have to find, now I have to find that what is u 0 comma y. U 0 comma y is that by putting x equal to 0 I get that sine of 0 minus y, that is sine of minus y, which is minus sine y. So my answer is option B, minus sine y. So u of 0 y is, so option B is correct. So with this I solved the problem 3. So now I will solve problem number 4, that is on implicit function theorem. Problem number 4 is on implicit function theorem. That is, consider the function phi of xy equal to y square plus y plus x minus 1, which is equal to 0. So which of the following statements are true about phi? So my which of the following statements are true? I have to verify each and every statements. First statement is that implicit function theorem guarantees Implicit function theorem. From the implicit function theorem, it guarantees that y can be expressed as a function of x in the neighborhood of the point 5 by 4, comma, minus r. So implicit function theorem that y sorry y can be expressed as a function of x in a neighborhood of 5 by 4, comma, half. I am writing short notation for neighborhood as nbt of 5 by 4, comma, minus half. Now the second option is, I am writing it in the separate page for simplicity. So the second option B is that y can, by implicit function theorem, it guarantees that y can be expressed as a function of x in the neighborhood of minus 1, comma, 1. So only the point changes. So implicit function theorem guarantees that y can be expressed as a function of x in the neighborhood of the point minus 1, comma, 1. Option C is option C is that implicit function theorem is not applicable at 1, comma, 0. And option D is that implicit function theorem guarantees that x can be expressed as a function of y in the neighborhood of 1 minus 1, comma, 1. Here is x. X can be expressed as a function of y. So implicit function theorem guarantees that x can be expressed as a function of y in the neighborhood minus 1, comma, 1, in the neighborhood of that point I write it as pt t minus 1, comma, 1. So now we will use what is the application of implicit function theorem. So my phi is a function. Clearly phi is a continuously differentiable function because it is a polynomial in x and y. So phi of xy is given as y square plus y plus x minus 1, which is equal to 0. So I have to check that if phi satisfies some properties, then phi of xy equal to 0 can be written as y equal to some function of x, or x equal to some another function of y. So what are the conditions? The condition is that if phi is at that point where in the neighborhood of that point we are explicitly find that function, if phi is equal to identically equal to 0 at that point, and del phi by del y, that is at that particular point, if it is non-zero, then I can say that phi can be written as a phi, function of single variable, that is y can be written as a function of x from phi xy equal to 0. So the two condition is that I have to check that phi at that point a comma b, suppose say phi is a comma b is equal to 0, and del phi of del y at that point a comma b, if it is non-zero, then by implicit function theorem I can say that phi of xy equal to 0 can be written as y equal to some function of x in that neighborhood of the neighborhood of a comma b. Now I will check these properties for this particular phi function around the points that are given. So for my first option is that point is point a comma b is 5 by 4 comma minus half. So I will check at phi at 5 by 4 comma minus half is what? That is y square means minus half square, it is plus 1 by 4 plus y, that is minus half, plus 5 by 4 minus 1. So it gives that 1 minus 2 plus 5 minus 4. So that gives 6 minus 6 equal to 0. So first condition satisfies. So that means that 5 by 4 comma minus half is on the curve phi xy equal to 0. That means this point a comma b, no, 5 by 4 comma minus half is on the curve. Now I will check that another property, that del phi upon del y at that point 5 by 4 comma minus half is what? Is 0 or non-zero? If it is non-zero, then we have that answer. Del phi del y is 2y plus 1. Sorry. Uh, two y plus 1 at at 5 by 4 comma minus half, so that is equal to 2 into minus half plus 1. So it gives that minus 1 plus 1, because 2 to cancel out here, so I get 0, but it does not satisfy the statement of implicit function theorem, so I cannot say that implicit function theorem is not satisfied here. I can say that implicit function theorem is not satisfied. Implicit function statement of implicit function theorem. Implicit function theorems. Okay, statement of implicit function theorem is not satisfied. So option A is not true. So option A I make not true. Now for option B, I will check again that same thing around the point minus 1 comma 1. So phi at minus 1 comma 1 is 1 squared is 1 plus 1 minus 1 minus 1, that is 0. So first statement of implicit function theorem satisfied. Now that means that minus 1 comma 1 is on the curve phi xy equal to 0. Now Now we'll check that del phi upon del y at minus 1 comma 1 is 0 or non-zero. So del phi upon del y at minus 1 comma 1 is 2y plus 1 at minus 1 comma 1. So if x value is minus 1, y value is 1. So I will put y equal to 1. So 2 into 1 plus 1, that is 3, which is a non-zero quantity. So I can say that by implicit function theorem, so by implicit, the statements of the implicit function theorem are satisfied. So by implicit function theorem, so by implicit function theorem, y can be expressed as a function of x in the neighborhood of the point minus 1 comma 1. It is y can expressed y can be expressed as a function of x in a neighborhood of minus 1 comma 1. So option B is true. Option B is right. Now for option C, I will check the same property around the point 1 comma 0. For option C, phi, option C, phi at 1 comma 0 is 0 plus 0 plus 1 minus 1, which is 0. So the first statement of implicit function theorem satisfies, that is 1 comma 0 is on the curve phi xy equal to 0. Now for the second statement, del phi upon del y at 1 comma 0, which is 2y plus 1 at 1 comma 0, that is 2 into 0 plus 1, that is 1, which is non-zero. So it shows that the implicit function theorem is applicable, but in the option it is given that implicit function theorem is not applicable, so option C is false. So but this shows that, so but in the option it is given that implicit function theorem is not applicable, so option C is false. Now for option D, I will check the same properties, but it is given that option D is that x can be expressed as a function of y in the neighborhood of minus 1 comma 1. So I already checked that minus 1 comma 1 is on the curve. Let me just clear this. From option A, B, I already checked that minus 1 comma 1 is on this curve, but again I am writing this phi at minus 1 comma 1 is 1 plus 1 minus 1 minus 1, that is 0. So minus 1 comma 1 is on the curve, lies phi of x comma y equal to 0. Now I have to check that x can be expressed as a function of y. So here I have to consider del phi upon del x, not del phi upon del y, this thing. So here I will consider del phi upon del x. So del phi upon del x at minus 1 comma 1 is 1, because phi is y square plus y plus x minus 1. So del phi upon del x is only 1, the value at minus 1 comma 1, it is constant function, so it gives 1, which is non-zero. So that means implicit function theorem is applicable. So by implicit function theorem, x can be expressed as a function of y in the neighborhood of minus 1 comma 1. So option D is correct. By implicit function theorem, x can be expressed as a function of y in the neighborhood of minus 1 comma 1. So option D is correct. So here the correct options are option B and option D. And clearly for D, I can say that x square x equal to 1 minus y square. That is the function. That is, suppose clearly phi of xy equal to 0 means y square plus y plus x minus 1 equal to 0, which implies that x equal to 1 minus y square. That is, clearly x can be written as a function of y in the neighborhood of minus 1 comma 1. So options B and D are correct. Option B and option D are the correct options. So with this, I am closing this session. Thank you.